What if Mars was not always a frozen desert, but once held rivers, lakes, and perhaps even the right conditions for life? Tonight, we'll travel through 4.5 billion years of Martian history, from its violent birth to the mystery hidden inside its ancient rocks. Welcome to Sleepy Cosmic Lore. About 90% of viewers are not subscribed, so helping us reach 1,000 subscribers would mean more than you know. Thank you for being here. Now let's begin. Long before Mars became a silent red world, it began inside a place where nothing was quiet. About 4.6 billion years ago, the Sun had only recently ignited at the center of a vast, rotating cloud of gas and dust, and around it stretched a violent disk filled with shattered minerals, metallic grains, frozen compounds, and countless fragments moving on intersecting paths. There were no planets yet, only collisions. Some particles struck and bounced apart. Others fused, forming larger bodies that pulled in still more material. Gravity slowly turned disorder into structure, but the process was anything but gentle. Every world in the inner solar system was assembled through repeated impacts, and Mars was born from that same storm of destruction. The atoms that would eventually form its mountains, plains, atmosphere, and perhaps even the chemistry needed for life were once scattered through this disk as debris from older stars. Iron had been forged inside stellar cores. Elements such as silicon, oxygen, magnesium, and sulfur had been expelled by stars that died before the Sun existed. Mars was not created from nothing. It was built from the remains of ancient suns, gathered grain by grain, until those grains became a planet. At roughly 1.5 times Earth's distance from the Sun, matter began collecting into small rocky bodies known as planetesimals. Each new collision released heat. As the growing object became larger, its gravity strengthened, increasing both the speed and violence of later impacts. Eventually, one body began to dominate its region. This was the planetary embryo that would become Mars. Evidence preserved in Martian meteorites suggests that Mars formed unusually quickly, perhaps reaching much of its final mass within only a few million years after the solar system began. In astronomical terms, this was almost immediate. Earth continued growing through larger and larger collisions for tens of millions of years, but Mars appears to have stopped early, as though the construction of the planet had suddenly been abandoned. That early interruption may explain almost everything that followed. Mars contains only about 1/10 of Earth's mass and has roughly half Earth's diameter. It is far larger than an asteroid, yet much smaller than Earth or Venus. Some scientists, therefore, describe it as a stranded planetary embryo, a world that began growing towards something larger but was deprived of the material needed to finish. The reason may lie with Jupiter. As the giant planet formed farther from the Sun, its gravity could have disturbed the distribution of rocky material, limiting how much remained available in the region where Mars was growing. Different models disagree on the exact sequence. In some, Jupiter shifted inward and then outward early in solar system history, scattering matter and leaving the Martian zone unusually empty. In others, the original disk simply contained less material near Mars's orbit. The details remain debated, but the outcome is written clearly in the planet's size. Mars became large enough to develop a complex interior, volcanoes, an atmosphere, and flowing water, yet small enough to lose many of those advantages over time. Its fate may have been decided before its surface had even fully formed. As material continued to crash into the young planet, the energy of impact was converted into heat. Radioactive elements inside Mars added still more. The early world may have been covered partly or almost entirely by molten rock, a deep magma ocean glowing beneath an atmosphere thick with vaporized material. This was not yet the Mars of red deserts and cold valleys. It was an incandescent sphere, its surface repeatedly melted, shattered, and remade. Heavy elements such as iron and nickel sank toward the center, forming a metallic core. Lighter silicate material rose above them, creating the mantle and, eventually, the first crust. This internal separation released additional heat and established the layered structure Mars still possesses today. At the center lay a core rich in iron, but also containing lighter elements such as sulfur. Around it moved a vast mantle of hot rock. Above that, cooling material formed a primitive crust whose surviving fragments would become some of the oldest terrain in the solar system. Mars's rapid formation gave it an early beginning, but its small size meant that it also began losing heat more efficiently than Earth. A small body has more surface area relative to its volume, allowing internal warmth to escape faster. This simple geometric fact would later influence its volcanoes, magnetic field, atmosphere, and ability to preserve liquid water. Yet, in the beginning, the interior was still extremely active. Molten iron moving within the core likely generated a global magnetic field, perhaps strong enough to surround the young Mars with an invisible shield. Remnant magnetism detected in ancient southern crust suggests that such a field once existed, although scientists are still working to determine exactly when it began and how long it lasted. A magnetic field does not automatically make a planet habitable, but it can help protect an atmosphere from charged particles flowing outward from the sun. On early Mars, that shield may have been one of the quiet conditions allowing the planet to become more Earth-like than it appears today. Above the cooling crust, the first atmosphere was being created. Some gases may have been captured directly from the disk around the young sun, but much of the early atmosphere probably came from the planet itself. Volcanoes and molten rock released water vapor, carbon dioxide, nitrogen, sulfur compounds, and other gases trapped in the interior. Impacts delivered additional volatile material, though they could also blast atmospheric gases back into space. The result was a constantly changing envelope around the planet, built and damaged at the same time. The young sun was dimmer than it is now, yet it was also far more active, producing intense ultraviolet radiation and powerful eruptions. Mars had to hold its atmosphere against both its weak gravity and the violence of its star. Whether it succeeded for hundreds of millions of years, or only in unstable intervals, remains one of the central problems in reconstructing its early climate. The oldest period of Mars is frustrating because very little of its original surface remains untouched. On Earth, plate tectonics continually recycles crust into the mantle, erasing most rocks from the planet's earliest history. Mars lacks the same global system of moving plates, so far more ancient terrain has survived, especially in the southern highlands. But survival does not mean preservation without damage. Early Mars endured repeated bombardment by asteroids and planetary fragments. Each major impact excavated deep layers, melted rock, altered the atmosphere, and covered older landscapes beneath new debris. Some collisions may have been so enormous that they reshaped entire hemispheres. The striking contrast between Mars's heavily cratered southern highlands and its lower, smoother northern plains may be related to one colossal impact, though internal geological processes have also been proposed. If a giant body truly struck northern Mars, the event would have been almost beyond imagination. A collision powerful enough to remove or deform a huge section of crust and leave behind a depression spanning much of the planet. But even that would not have been the end. Mars was repeatedly wounded, and each wound became part of the geography later explorers would study. The impacts were destructive, yet they may also have created temporary environments where water could exist. Heat from collisions could melt buried ice, drive hydrothermal circulation through fractured rock, and release gases into the atmosphere. On a young planet, catastrophe and opportunity were often the same event, viewed from different timescales. A collision might sterilize the surface nearby, then leave behind warm, water-filled fractures that remained chemically active long after the sky cleared. This is one reason early Martian history cannot be divided neatly into a hostile beginning followed by a habitable age. The conditions may have overlapped. Fire, water, impact, and cooling were all operating together. As the surface lost heat, the magma ocean began to harden. A dark crust spread across the planet. Water vapor in the atmosphere could condense where temperatures and pressure allowed, falling as rain or snow, freezing into the ground, or collecting in low areas. We cannot yet picture this transition with certainty. Mars may have entered a persistently cold state almost immediately, with water locked mostly as ice and released only during warmer episodes. Or the early atmosphere may have been thick enough, at least for a time, to support rainfall, lakes, and flowing rivers. The geological record contains evidence that liquid water eventually became widespread, but the exact climate that sustained it is still disputed. Carbon dioxide alone may not have produced enough greenhouse warming under the faint young sun. Other gases, high-altitude clouds, volcanic activity, impacts, or combinations of these factors may have supplied temporary warmth. The problem is not whether ancient water existed. The valleys, sediments, altered minerals, and lake basins make that increasingly difficult to deny. The mystery is how Mars maintained the conditions that allowed that water to move. Beneath this question lies an even deeper one. Did Mars become habitable because planetary evolution naturally pushes rocky worlds toward water and chemistry? Or was its brief promise the result of a rare chain of accidents? Its rapid birth gave it internal heat. Its early volcanoes supplied gases. Its magnetic field may have protected the atmosphere. Its impacts delivered energy and perhaps additional water. For a while, all these systems may have aligned, yet the planet had also been born too small. Its gravity was weaker, its interior would cool faster, and its protective field would not last forever. Mars, therefore, carried two futures from the beginning, one in which rivers spread across its surface, and another in which those rivers would eventually vanish. The remarkable part is that the first future seems to have happened at all. By the time the earliest crust stabilized, Mars was no longer merely a cooling ball of rock. It had become a functioning planet with a core, mantle, crust, atmosphere, volcanoes, impacts, and a growing inventory of water. The ingredients were present, but they had not yet settled into a peaceful world. Above the surface, asteroids still crossed the sky. Below it, magma continued to rise. Across the planet, newly formed landscapes were being erased almost as quickly as they appeared. Somewhere in that chaos, the foundations of ancient rivers and lakes were being laid. Mars had survived its birth, but the next stage would test whether it could become something far more extraordinary. Not simply a planet made from the ruins of the solar system, but a world where water could remain long enough for the first uncertain possibility of life to emerge. The age that followed was not a calm beginning, but a long struggle between destruction and renewal. A time when Mars was repeatedly shattered, flooded, buried, heated, and remade. Scientists call much of this ancient interval the Noachian period, beginning more than 4 billion years ago and fading roughly 3.7 billion years ago, although the exact boundaries remain uncertain because Mars does not provide a perfectly preserved calendar. Instead, its history must be read through overlapping craters, buried valleys, altered minerals, and layers of rock that survived where entire landscapes did not. The oldest regions, especially across the southern highlands, still carry the scars of this era so densely that almost every surface appears to sit on top of an earlier wound. To stand there would have been to watch a sky that was never entirely safe. Asteroids and planetary fragments continued to cross the inner solar system, and some struck Mars with enough force to excavate holes hundreds or even thousands of miles wide. The Hellas Impact Basin, one of the largest visible structures on the planet, plunges several miles below the surrounding terrain and spans more than 1,000 miles from side to side. Its creation would have released energy on a scale no human disaster can meaningfully compare with. Rock would have melted instantly. Shock waves would have traveled through the crust. Debris would have risen above the atmosphere before falling across distant regions. For a time, the sky may have glowed with dust and vaporized stone. Yet Hellas was not alone. Argyre and Isidis preserve evidence of other enormous collisions, each one powerful enough to reorganize drainage patterns, disturb the interior, and alter the atmosphere. These impacts did more than leave circular scars. They changed where water could collect, where lava could rise, and where heat could survive beneath the surface. A basin formed by violence could later become a reservoir. Fractured rock could become a pathway for hot water. The same event capable of destroying any fragile chemistry nearby might also create a hydrothermal system that remained active for thousands or perhaps millions of years. Early Mars was full of these contradictions. Catastrophe did not simply erase possibilities. Sometimes it created new ones. That is why the oldest Martian terrain cannot be understood as a dead battlefield. It was a dynamic world in which every impact opened the crust, released heat, and forced buried materials to interact in new ways. At the same time, volcanoes were reshaping the planet from within. Vast quantities of molten rock rose toward the surface, building broad volcanic provinces and releasing gases into the atmosphere. Carbon dioxide, water vapor, sulfur compounds, and smaller amounts of other gases escaped from the interior through eruptions and fractures. These emissions may have thickened the atmosphere for a time, trapping heat and changing the chemistry of the sky. But volcanic gases did not guarantee a warm climate. Sulfur compounds, for example, could contribute to warming under some conditions, while forming reflective particles that cooled the surface under others. Mars may have swung between these effects, warmed by one eruption and dimmed by the haze that followed. The climate was likely not a single stable state, but a sequence of episodes, some lasting long enough to carve rivers, others ending before the water had time to travel far. This uncertainty sits at the center of early Martian history. The landscape records flowing water on a massive scale, yet climate models have struggled to keep the surface warm enough for that water to remain liquid under the faint young sun. Around 4 billion years ago, the sun produced less energy than it does today. A thick carbon dioxide atmosphere could have helped, but perhaps not always enough. Additional warming may have come from hydrogen released during volcanic activity, from methane under certain chemical conditions, from high clouds that trapped infrared heat, or from repeated impacts that temporarily heated the atmosphere. None of these explanations has solved the problem completely. It is possible that Mars was warm and wet for long stretches, with rainfall feeding rivers and lakes. It is also possible that it remained mostly cold, storing water as ice until volcanic eruptions, orbital changes, or impacts triggered brief periods of melting. The rocks seem to preserve evidence that can support parts of both pictures. Valley networks across the ancient highlands resemble branching river systems, some beginning in broad upland regions and joining downstream in patterns difficult to explain without precipitation or widespread snowmelt. Elsewhere, giant outflow channels look less like ordinary rivers and more like the aftermath of sudden floods, perhaps released when underground water broke through frozen ground. These two kinds of features may not come from the same climate. One suggests water moving repeatedly through organized drainage systems. The other suggests enormous but short-lived releases. Mars may have experienced both, separated by millions of years, or occurring in different regions at the same time. The planet's surface was not behaving as a single, uniform environment. High elevations, deep basins, volcanic plateaus, and impact-fractured crust could each respond differently to the same atmosphere. Some areas may have remained frozen, while others briefly held lakes. Some valleys may have carried water seasonally, while others formed during rare climatic crises. Beneath the visible channels, the minerals tell an even quieter story. Ancient Martian rocks contain clays, known scientifically as phyllosilicates that generally form when water interacts with rock over extended periods. Their presence matters because a flood can carve a channel quickly, but changing the chemistry of minerals often requires a longer relationship between water and the crust. Clay-rich regions suggest that early Mars was not merely splashed by occasional disasters. In at least some places, water remained long enough to alter the rocks themselves. These environments may have been chemically mild compared with the more acidic conditions that became common later. On Earth, clays can trap organic molecules and preserve delicate traces of past environments. That does not mean Martian clays contain evidence of life, but they are among the most valuable places to search because they record a time when water and stone were in sustained contact. The oldest crust, therefore, holds two histories at once: the violent record of impacts above and the slower record of chemical change within. While craters count the blows Mars received, clays reveal what happened during the quieter intervals between them. One of the greatest mysteries of this age lies in the dramatic difference between the planet's hemispheres. Much of the southern half is high, rugged, and densely cratered, while the northern lowlands are smoother and sit several miles lower. This contrast, called the hemispheric dichotomy, is among the largest geological features in the solar system. Its origin remains unsettled. One possibility is that a gigantic impact struck early northern Mars, removing or thinning vast amounts of crust and creating an immense low basin. Another possibility is that internal convection shaped the crust unevenly, raising one hemisphere while thinning the other. Later volcanism and sedimentation then modified the difference, making the final pattern more complicated than any single event. If the impact explanation is correct, the collision would have been so large that it changed the basic architecture of the planet. It may have disturbed the mantle, influenced volcanic activity, and created a depression where water naturally gathered. That possibility leads directly to another controversy: whether the northern plains once held an ocean. Several proposed ancient shorelines have been mapped around the lowlands, and some sediments appear consistent with large bodies of standing water. Yet the supposed coastlines are not always level today, and their shapes can also be explained by later volcanic, tectonic, or erosional processes. Mars's crust may have shifted after the water disappeared, warping an originally level shoreline, or there may never have been one continuous ocean at all, only temporary seas and interconnected basins. The evidence is suggestive, but not decisive. What is clear is that the northern lowlands offered an enormous place for water to collect, if enough of it existed on the surface. Rivers flowing out of the southern highlands would naturally descend toward this lower hemisphere, carrying sediment, salts, and dissolved minerals with them. If an ocean formed, it may have been cold, partly frozen, and short-lived by planetary standards. Even so, its existence would transform how we imagine early Mars. A world with regional lakes is intriguing. A world with an ocean begins to resemble a second, incomplete version of Earth. The impacts themselves may have repeatedly influenced that ocean or those seas. A large collision into ice-rich crust could release vast quantities of vapor, create rainfall, and produce temporary greenhouse warming. For years or centuries afterward, water might move across the surface more freely. But impact-generated warmth fades quickly on geological timescales. Dust eventually settles. Vapor freezes or escapes. The planet returns to its underlying climate. This raises a question that runs through every attempt to reconstruct Noachian Mars. Were the rivers evidence of a stable world, or were they the brief afterglow of repeated disasters? Long-lived lakes, thick sediment deposits, and widespread clay formation argue that some wet environments persisted. Yet the lack of a fully convincing warming mechanism suggests that Mars may never have enjoyed the kind of steady climate Earth developed. Perhaps habitability existed not as one global condition, but as a network of refuges that appeared, vanished, and returned. A crater lake might last for hundreds of thousands of years, while the surrounding plateau remained frozen. A hydrothermal system might continue beneath an impact basin after surface water disappeared. A volcanic region could release enough heat to melt buried ice and feed rivers locally. From the viewpoint of a microorganism, if one ever existed, the entire planet did not need to be warm. Only one environment needed to remain stable long enough. That possibility gives this violent age its deepest significance. Mars was not simply enduring bombardment while waiting for a better future. The bombardment, volcanism, groundwater, and atmospheric changes were creating countless experiments in habitability. Some lasted briefly. Others may have survived through long geological intervals. Each basin, fracture system, and mineral-rich lake represented a different combination of water, heat, chemistry, and time. Most would leave no obvious trace. A few became landscapes that spacecraft can still recognize billions of years later. By the end of this era, Mars had accumulated an astonishing network of scars and waterways. Great basins dominated the horizon. Rivers crossed ancient highlands. Floods had torn through frozen ground. Clay minerals had formed in wet environments. Sediment had begun to gather in lakes, where fine particles settled slowly through quiet water. The planet was still dangerous, still unstable, and still vulnerable to the next impact. But it was no longer merely a world of fire. Water had become one of its defining forces. What remained uncertain was whether that water appeared only in brief flashes or stayed long enough to transform chemistry into something more. The answer would not be found in the largest crater or the deepest flood channel, but in the places where water slowed down, where rivers entered basins, and where layer after layer of sediment began preserving the history of a world that may have been approaching its most promising moment. By the time the first great river systems began cutting across Mars, the planet had already become a world of contrasts. High volcanic plateaus rising above immense lowlands, ancient craters collecting water in their depths, frozen ground locking away hidden reservoirs, and a sky that may have shifted between thick clouds, dust, snow, and long periods of bitter cold. Yet, across this unstable landscape, water found paths. It ran downhill through fractures, spilled over crater rims, gathered into lakes, and carried sand, clay, and dissolved minerals across distances that can still be traced billions of years later. From orbit, many of these valleys look strangely familiar. They branch like trees, with narrow channels joining larger ones, exactly the kind of pattern created when water repeatedly drains across a broad surface. They are not isolated scratches left by a single flood. Some form entire networks extending for hundreds of miles, beginning on high ground and descending toward basins where lakes once stood. Their shapes suggest a landscape organized by gravity and flowing water, a planet where precipitation, melting snow, groundwater, or some combination of all three fed rivers often enough to reshape the land. But the closer scientists look, the more complicated the picture becomes. Mars preserves evidence not of one simple wet age, but of many different kinds of water moving under different conditions. In some places, rivers seem to have flowed gradually, building channels through repeated seasons or long climatic intervals. In others, enormous outflow channels appear to have been carved by sudden releases so violent that they make Earth's largest known floods seem restrained. These channels stretch miles across, with streamlined islands and eroded surfaces showing where unimaginable volumes of water once rushed through. The source may have been groundwater trapped beneath frozen crust until pressure broke the surface open. It may have been ice melted by volcanic heat. It may even have been water released when an impact fractured deep underground reservoirs. Whatever triggered these events, they did not resemble ordinary rivers. They were planetary-scale escapes, water bursting from confinement and racing toward lower ground before freezing, evaporating, or disappearing into the soil. Yet the gentler valley networks tell a different story, and it is this difference that keeps the climate of ancient Mars unresolved. A sudden flood can be explained by one eruption, one impact, or one collapse of buried ice. A branching river system is harder. It suggests water arriving across a wide region again and again. On Earth, rainfall produces exactly this kind of drainage pattern. But rainfall on Mars requires an atmosphere warm and dense enough for liquid water to survive at the surface. Some researchers therefore argue that early Mars experienced extended warm periods when clouds gathered, rain or snow fell, and rivers flowed beneath a thicker sky. Others believe the planet remained mostly frozen, with snow accumulating in the highlands, until rare warming events melted it. In that colder model, the rivers were real, but the climate behind them was temporary. Mars may have remained locked in ice for long stretches, then awakened for a few thousand or a few million years before freezing again. The geological evidence does not yet force one single answer. Instead, it seems to preserve a world that may have moved between these states. The most revealing locations are often not the channels themselves, but the places where the water slowed. When a river enters a lake, it loses speed and drops the material it has carried. Sand settles first, then finer mud and clay. Over time, these deposits build outward into a fan-shaped delta, layer upon layer, creating a natural archive of everything the river passed through upstream. Mars contains several structures that strongly resemble ancient deltas. Their preserved channels split into smaller branches near the edge of crater basins, while sediment spreads across what would once have been the lake floor. These formations matter because a delta cannot be created by water merely flashing across the ground for a few moments. It usually requires repeated flow, enough sediment, and enough time for the deposits to accumulate into a recognizable shape. The exact duration is difficult to determine. Some Martian deltas may have formed in relatively short but intense episodes. Others may record rivers returning over thousands or even millions of years. Either way, they show that water did more than pass through. In some places, it established a landscape. The ancient lake basins of Mars reveal that landscape in remarkable detail. Craters that once formed as wounds later became containers, trapping rivers and preserving sediments that would otherwise have been scattered. Some basins show channels entering through one side and exiting through another, suggesting that the lake rose high enough to overflow. This is especially important because an overflowing lake was not simply a temporary puddle. It was part of a larger connected system, receiving enough water to fill, spill, and continue feeding valleys downstream. Other craters appear to have held closed lakes with no outlet, where water ended its journey and slowly vanished through evaporation, freezing, or seepage into the ground. In those closed basins, salts and minerals may have become concentrated as the water disappeared, preserving evidence of changing chemistry. Each lake tells a slightly different story. Some may have been fresh and long-lived. Some may have been shallow and seasonal. Others may have become increasingly salty as the climate dried. The rock record suggests that Mars did not lose its water in a single clean transition. Lakes expanded, contracted, returned, and vanished at different times. This is why the planet's dry valleys can be deceptive. What now appears to be an empty depression may once have contained shorelines, muddy shallows, deeper water, and streams feeding it from distant hills. The silence of the modern landscape hides how active the system once was. Even the stones inside these ancient channels carry evidence of movement. Curiosity photographed rounded pebbles in Gale Crater, their sharp edges worn down in a way that strongly suggests they were transported by flowing water. On Earth, rocks become rounded as they tumble along streambeds, repeatedly striking one another. The Martian pebbles were not found beside an existing river, but embedded in rock formed from ancient gravel. Their shape preserves motion that ended billions of years ago. From their size and arrangement, researchers inferred that the water may once have flowed with the strength of a shallow stream, perhaps deep enough to reach a person's ankles or knees in some locations. That image is almost disturbingly ordinary. Not a catastrophic wall of water, not a boiling flood born from an impact, but a river moving stones beneath a Martian sky. The evidence from sedimentary layers adds another dimension. Inside several craters, thin bands of rock stack on top of one another like pages in a closed book. Some formed when mud settled in quiet water. Others came from sand carried by wind or streams. Changes in grain size and mineral content reveal shifts in depth, chemistry, and climate. At Gale Crater, the lower slopes of Mount Sharp contain layers representing environments that changed over enormous spans of time. A lake may have occupied the crater repeatedly, retreating during drier intervals and returning when conditions allowed. The mountain itself was built gradually from sediments deposited within the basin, then exposed as wind removed surrounding material. What looks today like a solitary mountain is partly the remains of an ancient environmental record. As curiosity climbed through those layers, it moved forward through Martian history, leaving clay-rich rocks associated with long-standing water and approaching sulfate-rich layers linked to more evaporative, increasingly dry conditions. The transition was not perfectly sudden, and that is precisely what makes it valuable. Mars appears to have dried through a complicated sequence rather than a single irreversible moment. Water persisted in some regions even as others became hostile. Rivers may have continued flowing locally after the broader climate had already begun to fail. One of the deepest puzzles is how much water Mars actually possessed. The valleys and lakes show that it had enough to reshape vast areas, but estimating the total volume is difficult because much of the original water is gone, frozen underground, trapped in minerals, or buried beneath later deposits. Some reconstructions suggest that if all ancient Martian water had been spread evenly across the planet, it could have formed a global layer hundreds of feet deep, perhaps much more under certain models. But that does not prove the existence of a permanent global ocean. Water may have been distributed unevenly, locked mostly as ice, and released only during warmer intervals. The northern lowlands remain the obvious destination for rivers descending from the highlands, and proposed shorelines continue to fuel the idea of an ancient sea. Yet the evidence is incomplete. Some possible coastal features may have been distorted by later crustal movement. Others may have been produced by volcanic flows or ice-related processes rather than waves. The ocean remains plausible, but not settled. Even without it, the confirmed lakes and river systems already reveal a planet far more active than the one seen today. The chemistry of those waters may have mattered as much as their volume. Clay minerals indicate that some early environments were relatively gentle, with water interacting with rock under conditions that could preserve complex molecules. Later waters in other regions became more acidic or salty, possibly as volcanic gases altered the atmosphere and evaporation concentrated dissolved chemicals. For life as we understand it, neither acidity nor salt necessarily ends the possibility of survival. Organisms on Earth inhabit both. The larger issue is stability. Chemistry needs time. Organic molecules must remain intact long enough to react. Energy must be available without destroying everything it helps create. Water must persist or return often enough for complexity to build. Ancient Martian river valleys show that the planet repeatedly supplied one of the most important ingredients, but they cannot reveal by themselves whether the next step occurred. That answer may lie in the mud deposited at the bottom of a lake, protected from radiation and sealed inside rock. It may lie in clay carried into a delta, where organic material could have been trapped between microscopic mineral layers. It may lie in sediments so fine that only instruments on another world can detect what they preserved. The rivers, therefore, matter not merely because they prove Mars was wet. They connect the entire planet's history. They carried material from volcanic uplands into quiet lakes. They exposed buried minerals, mixed chemicals from distant regions, and created environments that changed from fast-moving channels to calm, shallow water. A single river could link many different habitats along its course. If primitive chemistry ever began somewhere upstream, the current might have carried its traces into a basin where they could survive. And if microbial life had already appeared, a delta would have been one of the best places for its remains to accumulate. That is why later missions would not search randomly across the Red Desert. They would aim for ancient lake beds, clay-rich layers, and preserved deltas. The dry channels had already shown scientists where the water went. The sediments at their ends might reveal what the water once contained. Around 3.5 billion years ago, certain regions of Mars were approaching the most important moment in their history. Rivers were entering craters. Lakes were standing beneath the sky. Minerals were settling through the water. Carbon-bearing compounds were present. Energy came from sunlight, volcanic heat, impacts, and reactions within rock. The planet had assembled many of the conditions associated with habitability, perhaps for longer than anyone once imagined. Yet there is a haunting gap between a habitable environment and an inhabited one. The rivers can lead us to the edge of that gap, but they cannot carry us across it. To go farther, the story must leave the channels and descend into the ancient lakes themselves, into the mud and stone formed during the narrow window when Mars may have come closer than ever to becoming a living world. Around 3.5 billion years ago, there were places on Mars where the difference between a dead planet and a living one may have narrowed to something almost impossible to see. Not a forest, not an ocean filled with creatures, not even a shoreline marked by anything larger than drifting sediment. If life existed there, it was probably microscopic, hidden in water, mud, mineral pores, or fractures beneath the ground. Yet the setting around it may have been surprisingly familiar. Rivers entered crater basins. Lakes spread across lowlands surrounded by dark volcanic rock. Fine clay settled slowly through the water. Sunlight crossed a sky denser than the one Mars has today, and chemical energy moved through the boundary where water met stone. This was not a planet guaranteed to produce life. It was something more unsettling, a planet that appears to have possessed many of the right conditions, yet left no confirmed answer about what happened next. One of the clearest windows into that lost age lies inside Gale Crater, an impact basin roughly 96 miles wide near the Martian equator. Long after the collision that created it, water entered the depression and transformed it into a lake system. Streams carried gravel, sand, and mud down from the crater rim. Some of that material accumulated on the floor. Some was altered by water. Layer by layer, the basin began recording its own environmental history. Billions of years later, the Curiosity rover would cross those deposits and find rounded pebbles, ancient streambed gravel, mudstone, clay minerals, sulfur, nitrogen, phosphorus, carbon, and other ingredients associated with environments that could support microbial life. The important discovery was not a fossil or a biological molecule that proved organisms had been there. It was something more basic and, in a way, more profound. The lake did not appear to be chemically extreme from the beginning. At least during some intervals, its water may have been relatively calm, low in acidity, and capable of providing the elements and energy sources that simple organisms on Earth can use. A place does not need to look like modern Earth to be habitable. It does not need oxygen-rich air, green land, or warm tropical water. Microbes on our planet survive without sunlight, feeding on chemical reactions between water and rock. Others endure freezing conditions, high salt concentrations, darkness, and pressures that would kill most complex life. For early Mars, the most meaningful question is therefore not whether a human could have stood beside one of its lakes, almost certainly not without protection. The question is whether a microscopic organism could have lived there, reproduced, and persisted long enough to leave a trace. At Gale, the answer seems to be that the environment may have allowed it. The crater contained liquid water. It contained carbon-bearing material. It contained minerals that could participate in energy-producing reactions. Its sediments suggest that water returned or remained through multiple phases, rather than appearing in a single brief flood. This combination is why scientists use the word habitable, but that word must be handled carefully. A furnished house is not proof that anyone ever lived inside it. In the same way, a habitable lake is not proof that life occupied it. It only establishes that the door may have been open. Far away, Jezero Crater preserved another version of the same mystery. Jezero is smaller than Gale, but its landscape contains one of the most compelling ancient deltas yet identified on Mars. A river once cut through the crater wall and carried sediment into a standing lake. As the current slowed, the material spread outward, building a layered fan whose shape remained visible from orbit. The river later changed course across the delta, leaving channels, ridges, and deposits that record the movement of water through time. A second breach on the opposite side of the crater suggests that the lake may have filled high enough to overflow, connecting it to a larger drainage system. This matters because Jezero was not simply a hole where meltwater collected and vanished. It appears to have participated in a broader hydrological network, receiving water and, at least during some periods, releasing it downstream. Scientists estimate that the lake may have existed during the broad interval when Mars was shifting from a wetter ancient world toward a colder and drier one. Exactly how long it remained filled is still debated. Some features may have formed through intense episodes separated by dry gaps. Others suggest repeated or sustained flow. Either possibility offers time for chemistry to develop, but the distinction is important. A lake lasting millions of years provides one kind of opportunity. A lake appearing for centuries, freezing, vanishing, and returning provides another. Life might adapt to cycles if it already existed. The origin of life, however, may require stability, concentration, and repeated chemical steps that are easier to interrupt than to begin. Jezero's delta is valuable because deltas naturally collect evidence from a wide area. Everything washed down the river, mineral grains, salts, fragments of organic material, perhaps even traces of biological activity, if any existed upstream, could become trapped in fine sediment. On Earth, mudstone and clay-rich deposits can preserve organic molecules by shielding them from oxidation and binding them to mineral surfaces. Mars offers no guarantee that preservation worked the same way, especially after billions of years of radiation and chemical alteration. But the logic is strong enough that NASA sent Perseverance directly into the crater. The rover is not merely exploring an ancient lake. It is moving across a natural archive assembled by water when Mars may have been near the peak of its habitability. The water itself may have contained a changing mixture of dissolved elements carried from volcanic terrain, impact-altered crust, and weathered highlands. Iron, sulfur, magnesium, calcium, and carbon could participate in reactions that microbes on Earth use for metabolism. Sunlight may have supplied additional energy near the surface, though ultraviolet radiation under a thinner, ozone-free atmosphere would also have damaged exposed organic compounds. The safest environments may therefore have existed beneath shallow water, within sediment, or below the surface where rock provided protection. This creates a strange possibility. The best place for life to begin may not have been the most visually dramatic part of ancient Mars. It may have been a dark boundary, only inches below a lake bed, where water seeped through mineral grains and chemical differences created a steady source of energy. Or it may have been deeper, inside hydrothermal systems where heated groundwater circulated through fractured rock. Mars was still volcanically active, and residual heat from impacts and magma could drive these underground environments even when the surface climate became hostile. On Earth, similar settings support ecosystems that do not depend directly on sunlight. Whether they also helped life begin remains debated, but they demonstrate that a cold surface does not necessarily mean a biologically useless planet. The atmosphere above these lakes remains one of the hardest pieces to reconstruct. Mars needed enough pressure for liquid water to remain stable, but scientists do not yet agree on exactly how dense the atmosphere was or how long warm conditions lasted. Carbon dioxide was probably abundant compared with today, yet models suggest that carbon dioxide alone may not have kept the planet consistently warm beneath the fainter young sun. Additional warming could have come from hydrogen mixed into the atmosphere, clouds that trapped heat, volcanic gases, or short-lived changes following major eruptions and impacts. Another possibility is that much of Mars stayed cold, while ice accumulated in highlands and melted during favorable orbital cycles. In that picture, lakes such as those in Gale and Jezero were not permanent features beneath a mild climate. They were temporary worlds created during intermittent thaws. The geological record allows room for both sustained and episodic water, and Mars may have shifted between them. This ambiguity does not erase the evidence for habitability. It changes the kind of habitat being considered. A cold lake covered by ice can still contain liquid water beneath its surface. Ice can reduce evaporation, protect against radiation, and create a stable zone below, even when the air above is freezing. On Earth, microbial communities survive in subglacial lakes and beneath ice-covered environments that receive little light. Ancient Mars may have offered comparable refuges. The landscape could have looked lifeless from above, while remaining chemically active below. That distinction is crucial because our imagination is drawn toward open blue water, rain, and rivers shining beneath clouds. But biology does not require scenery. It requires access to usable energy, liquid water, essential elements, and enough stability to maintain complex chemistry. Around 3.5 billion years ago, at least some Martian basins appear to have brought those ingredients together. The planet had carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, the core elements used by life on Earth. It had minerals capable of storing and releasing chemical energy. It had sedimentary environments that could concentrate molecules rather than allowing them to disperse. It had protective spaces in mud, clay, and rock. What it may not have had was time in the right form. Mars was already losing atmospheric protection. Its climate was becoming less reliable. Lakes could shrink, freeze, or turn salty. Rivers could stop. Radiation could break down material left near the surface. Habitability may have existed as a collection of windows opening and closing across the planet, rather than one uninterrupted age. If life had already emerged early, it might have followed the retreating water underground. If it had not yet begun, each environmental collapse may have forced chemistry to start over. That difference could separate a living planet from one that remained permanently on the edge. There is also the possibility that the origin of life is easier than we think. On Earth, life appeared relatively early in the planet's history, though the exact timing and nature of the earliest evidence remain debated. If life tends to arise whenever water, rock, energy, and organic chemistry remain together long enough, then ancient Mars may have had multiple chances. Lakes, hot springs, hydrothermal fractures, wet sediments, and subsurface aquifers could each have hosted separate chemical experiments. But if life requires an extremely rare sequence of events, Mars may have possessed every visible ingredient while still missing one invisible step. This is what makes the planet more than a search for alien organisms. It is a test of whether habitability naturally becomes biology, or whether the distance between the two is far greater than it appears. By the time mud settled at the bottom of Gale and river sediment spread across Jezero, Mars had built environments where that question could be asked in physical form. The answer, if it was ever recorded, would not be written in bones or shells. It might survive as an unusual pattern of carbon, a mineral arrangement difficult to explain without metabolism, a concentration of organic molecules, or microscopic structures trapped inside ancient rock. Every one of those signs can also be produced or altered by non-living chemistry, which is why no single discovery is likely to settle the matter. Proving ancient life on Mars will require several lines of evidence pointing in the same direction and surviving every alternative explanation scientists can devise. For now, the most honest picture is also the most haunting. Around 3.5 billion years ago, rivers entered lakes beneath a changing Martian sky. Water moved through clay, mud, volcanic minerals, and fractured stone. The necessary elements were present, and several sources of energy were available. The planet was not alive, as far as we can prove, but neither was it the frozen desert we know today. It stood somewhere between possibility and silence, holding environments that might have supported the simplest forms of life, while leaving us no confirmed trace that they ever appeared. And as those lakes filled and emptied, another process had already begun beyond their shores. The conditions that made the surface habitable were weakening, slowly turning every river, every delta, and every sheltered lakebed into a race against a planetary transformation that life, if it existed, would somehow have to survive. If life ever began on Mars, it probably did not announce itself with movement, color, or anything that would have looked alive to human eyes. It may have started as a chemical imbalance inside a warm crack in the rock, a thin film left behind when water evaporated, or a cluster of carbon-rich molecules trapped against the surface of clay. At first, there would have been no cell, no genetic code, no clear boundary separating life from non-life. Only matter being pushed into greater complexity by sunlight, heat, minerals, and repeated contact with water. That first step is still mysterious even on Earth, where every organism alive today shares an ancestry stretching into a past that geology has almost completely erased. Mars gives us a second laboratory, one that stopped changing as violently as Earth did, and may have preserved portions of the experiment in ancient stone. The raw ingredients were not rare. Carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus existed in Martian rocks, water, and atmosphere, while organic molecules could have formed through non-living chemistry or arrived inside carbon-rich meteorites and interplanetary dust. Curiosity has confirmed that organic carbon survived in ancient Martian mudstone, including increasingly large and diverse molecules. But organic does not mean biological. In chemistry, it simply means compounds built around carbon, and nature can produce them without a living cell. The real challenge was not obtaining ingredients. It was persuading scattered molecules to meet, react, remain together, and eventually form a system capable of preserving information and making imperfect copies of itself. Water helped by allowing chemicals to move and encounter one another. But too much water may have created another problem: dilution. In a deep lake, useful molecules could drift apart faster than they combined. This is why some origin of life researchers are drawn to shorelines, volcanic pools, and shallow basins where water repeatedly advanced and retreated. During a wet phase, compounds would dissolve, spread, and mix. During a dry phase, evaporation would force them into close contact, increasing the chance that smaller units linked into longer chains. Laboratory work has shown that repeated wet-dry cycles can encourage the formation of biologically relevant building blocks and larger molecular structures under plausible prebiotic conditions. Although an experiment that works in a controlled setting does not prove the same sequence occurred on Mars. Ancient Mars may have offered countless versions of this cycle. A shallow lake could shrink under a colder or drier climate, leaving mineral-rich mud exposed to ultraviolet light. Snowmelt or groundwater might later refill it, washing the concentrated products into new pools. Salts within the sediment could draw moisture from the air or retain thin liquid films after open water vanished. Every return of water would rearrange the chemistry, destroying some structures while giving others another chance to grow. From a distance, this would look like a lake dying and returning. At the molecular scale, it could behave like a slow, natural machine, repeatedly sorting, concentrating, and testing combinations. The minerals beneath that water were not passive scenery. Clays have charged surfaces that can attract and organize organic compounds. Iron and sulfur-bearing minerals can transfer electrons, creating chemical gradients that simple organisms on Earth use as energy sources. Tiny pores inside rock can hold molecules close together and protect them from being swept away. A fracture only a fraction of an inch wide might have been more important than an entire open lake, because it could maintain a stable boundary between fluids of different temperature, acidity, and composition. Life, at its most basic, depends on boundaries and gradients. A modern cell uses a membrane to keep one chemical environment inside and another outside, then exploits the difference between them. Before true membranes existed, mineral walls and microscopic cavities may have performed part of that role. This is one reason hydrothermal environments remain such a powerful possibility. Where groundwater reached hot rock, it could rise again, carrying dissolved minerals and gases. When that fluid mixed with colder water, new minerals would precipitate, forming porous structures filled with chambers and channels. Experiments designed to imitate ancient hydrothermal systems show that vent-like conditions can generate organic compounds and create environments where prebiotic reactions may proceed. Though scientists continue to debate whether life was more likely to begin in deep water, in warm pools on land, or through several connected settings rather than one perfect birthplace. Mars may have contained both surface pools and underground hydrothermal networks, sometimes linked by impacts or volcanism. Water circulating through iron-rich rock could also drive reactions that released hydrogen, a fuel that certain microbes on Earth consume without sunlight. If early Martian chemistry learned to exploit such reactions, the first ecosystem might have existed underground from the beginning, hidden from the unstable climate above. That possibility changes the image of a living Mars. The most promising habitat may never have been a sunlit lake. It may have been a dark aquifer beneath it, warm enough to remain liquid and shielded from destructive radiation. Sunlight itself played a double role. Ultraviolet radiation can tear apart organic molecules, especially on an exposed surface without a protective ozone layer. Yet energy is also required to build complexity, and ultraviolet light can drive reactions that create useful compounds from simpler ones. The same force could therefore construct molecules in one setting and erase them in another. Mud, ice, water, and rock would control which outcome dominated. A molecule formed in a shallow pool might survive if it was quickly buried by sediment. Left exposed, it could be broken apart. Mars did not need uniformly gentle conditions. It needed small regions where destructive and constructive forces reached the right balance. Then came the harder leap, packaging chemistry into something that could evolve. One idea places information first, imagining molecules related to RNA that could both store instructions and assist chemical reactions. Another places metabolism first, suggesting that self-sustaining networks of reactions developed in mineral pores before anything like a genetic code existed. A third emphasizes primitive compartments, droplets or membrane-like bubbles that enclosed useful molecules, preventing successful combinations from immediately dispersing. Experiments have shown that plausible prebiotic molecules can spontaneously assemble into droplets or membrane-like structures, and some laboratory systems can grow, divide, or maintain chemical reactions. But none of this has recreated the complete origin of life or identified the exact route nature took. On Mars, these pathways may have competed rather than followed a clean sequence. A mineral surface could help form a chain-like molecule. A drying pool could concentrate it. A fatty compound delivered by a meteorite could surround it. Geothermal chemistry could provide energy. Most combinations would fail. Some would persist for a while and then collapse. The crucial breakthrough would be a system whose variations affected its survival, allowing successful arrangements to become more common. At that point, chemistry would begin behaving like evolution. But there is no agreed line marking the instant this happened, and the first evolving systems may have looked so unlike modern cells that even a perfectly preserved sample would be difficult to recognize. There is another possibility, stranger because it connects Mars directly to our own history. Impacts have blasted Martian rocks into space, and some of those rocks eventually reached Earth as meteorites. The reverse journey is physically possible as well, though less efficient. If microorganisms or prebiotic material could survive the initial shock, years in space, and atmospheric entry, then material might have moved between the young planets. This idea, known as lithopanspermia, does not explain how life began. It only changes the location of the first beginning. Mars may have seeded Earth. Earth may have seeded Mars, or both worlds may have developed chemistry independently. No evidence currently establishes any of these scenarios, and survival through the full journey remains a demanding chain of conditions rather than an easy passage. Still, the exchange of rocks means the histories of the two planets were never completely isolated. A discovery of ancient Martian life would therefore lead to an even more difficult question. Was it truly alien, or a distant branch of the same tree that includes us? The only way to distinguish those possibilities would be to recover evidence detailed enough to compare its molecular architecture, something no rover has yet done. For now, Mars offers ingredients, environments, and plausible pathways, not a confirmed origin. Ancient organic compounds show that carbon chemistry was present and could be preserved. Lakes and groundwater supplied places for reactions to unfold. Wet-dry cycles may have concentrated molecules. Mineral surfaces and hydrothermal pores may have organized them. Meteorites may have delivered additional material. Yet every one of these processes can stop before biology begins. A planet can be chemically rich and remain lifeless. That is the unsettling possibility Mars holds before us. Perhaps the universe easily creates worlds filled with water and organic matter, but almost never crosses the final distance to evolution. Or perhaps life begins readily, and Mars once carried a hidden biosphere, whose traces are now scattered through mudstone and buried fractures. If something did awaken there, it entered a world already moving toward crisis. The surface environment was becoming less reliable, the atmosphere more vulnerable, and the lakes increasingly temporary. Whatever life had achieved, whether only a fragile molecular system or a true population of microbes, it would soon face a test far more severe than its own creation, surviving the slow collapse of the planet that gave it a chance to exist. Mars did not die in a single afternoon. There was no final storm, no last river suddenly sinking into the ground, no moment when the planet changed from living possibility to frozen desert. Its decline unfolded so slowly that no observer standing beside one of its ancient lakes would have recognized the beginning. Water still moved through valleys. Volcanoes still released gas from deep below. Ice still melted during warmer intervals, feeding streams that returned to familiar channels. Yet beyond the clouds, an invisible defense was weakening, and with it, the entire surface environment was beginning to come apart. Early in its history, Mars appears to have possessed a global magnetic field generated by the motion of electrically conducting material inside its metallic core. Like the magnetic field around Earth, it may have formed a protective region that redirected much of the charged material flowing outward from the Sun. That protection was never perfect, and a magnetic field alone cannot preserve an atmosphere forever, but it can reduce the direct assault of the solar wind. Ancient rocks in the southern highlands still contain bands of remnant magnetism, as if parts of the crust froze while this planetary shield remained active. Other regions, especially those formed or altered later, carry far weaker magnetic signatures. From that pattern, scientists infer that the internal dynamo shut down very early, perhaps more than 4 billion years ago, although its exact timing and the reason for its disappearance remain uncertain. Mars may have cooled too quickly for the necessary motion inside the core to continue. A massive impact may have disrupted circulation. The mantle may have stopped removing heat from the core efficiently. Whatever the cause, the result was profound. Mars lost its global magnetic shield, while the young Sun was still far more violent than the star we know today. The solar wind is not an ordinary wind. It is a stream of charged particles moving through space at tremendous speed, carrying the Sun's magnetic influence with it. When these particles encountered the upper Martian atmosphere, they transferred energy to atoms and molecules, helping strip them away. Some atmospheric particles were pushed directly into space. Others were electrically charged, swept up by magnetic fields carried in the solar wind, and dragged down the long, invisible tail extending behind the planet. High-energy radiation could split water vapor into hydrogen and oxygen. Light hydrogen escaped most easily because Mars's gravity was weak, leaving behind heavier oxygen that could either escape more slowly or react with surface minerals. Over immense spans of time, these processes changed not only the thickness of the atmosphere, but the entire character of the planet. NASA's MAVEN spacecraft has observed atmospheric escape happening today and measured how strongly solar storms can increase the loss. Modern Mars is already thin and cold, so the present escape rate does not explain the ancient transformation by itself. But when researchers trace these mechanisms backward to a time when the Sun was more active and the Martian atmosphere was thicker, the cumulative effect becomes far more powerful. Mars did not simply run out of air. It leaked into space, atom by atom, storm after storm, across hundreds of millions of years. The evidence is written in isotopes, different versions of the same element with slightly different masses. Lighter isotopes escape more readily, leaving the atmosphere enriched in heavier ones. Measurements of argon, hydrogen, and other elements reveal this selective loss. allowing scientists to estimate how greatly the atmosphere changed. Water carries a similar signature. Martian water is unusually enriched in deuterium, the heavier form of hydrogen, compared with water on Earth. Ordinary hydrogen escaped more easily, so the water left behind became increasingly heavy. This does not reveal exactly how much water once covered the surface, because some became trapped as ice or locked inside minerals, but it shows that an enormous amount was removed from the active Martian system. The rivers did not disappear because every molecule of water vanished. They disappeared because the atmosphere could no longer support a stable world in which water could circulate freely between surface, sky, and ground. As pressure fell, liquid water became increasingly difficult to maintain. On modern Mars, exposed ice usually does not melt into a lasting pool. It tends to pass directly into vapor, while liquid water at the surface rapidly freezes, evaporates, or boils under the low pressure. Ancient Mars crossed toward this condition gradually. At first, lakes may have lasted for long intervals. Later, they may have become seasonal or episodic, appearing after volcanic eruptions, impacts, or orbital changes, and then fading when the temporary warmth passed. River systems that once received regular flow became dependent on rare events. A valley could remain dry for thousands of years, briefly carry meltwater, then fall silent again. This transition would not look like a planet dying all at once. It would look like reliability disappearing. Rain or snow became less frequent. Lakes failed to refill. Shorelines retreated. Water left salts behind as it evaporated, making the remaining environments more chemically extreme. At Gale Crater, curiosity has encountered a geological progression from clay-bearing layers associated with sustained interaction with water toward sulfate-rich rocks that often form under increasingly dry, evaporative conditions. The sequence is complicated, and local environments sometimes became wet again, but the broader movement is clear. Conditions that once supported stable lakes gave way to a harsher world where water was increasingly scarce, salty, and temporary. The sky itself may have changed color and clarity as the atmosphere thinned. Clouds could still form, and dust storms still moved across the planet, but the greenhouse effect weakened. Carbon dioxide froze at the poles during colder intervals. Water became concentrated as ice in the ground and at high latitudes. Mars's changing orbit and tilt would have shifted ice between regions, sometimes placing it closer to the equator than it is today. During warmer orbital phases, portions of that ice could melt or turn into vapor, creating brief returns of flowing water. These episodes may explain some relatively young channels and deposits, but they were no longer evidence of a healthy global climate. They were remnants of a broken cycle, short awakenings on a planet unable to sustain them. Mars's small size had become its deepest disadvantage. Its gravity could not hold light gases as effectively as Earth's, and its interior had lost heat rapidly enough to weaken the geological systems that might have renewed the atmosphere. Volcanoes did continue erupting for billions of years, and some Martian volcanic activity may be geologically recent, but the long-term output was not sufficient to rebuild what space weather removed. Earth also loses atmospheric particles, yet its stronger gravity, active interior, magnetic field, oceans, and carbon cycle help maintain a much thicker atmosphere. On Mars, those systems either weakened or never developed into the same self-reinforcing network. Once atmospheric loss pushed the planet beyond certain thresholds, each consequence intensified the next. Lower pressure made liquid water less stable. Less surface water weakened chemical weathering that could influence atmospheric gases. Cooling locked more water into ice. A colder, drier surface reduced the environments in which any hypothetical organisms could survive. This was not one cause acting alone, but a chain of failures, each narrowing the planet's options. The disappearance of the magnetic field is often described as the beginning of the end, but that explanation can be too simple. Venus has no Earth-like global magnetic field and still retains an extremely thick atmosphere, largely because it is more massive and possesses very different atmospheric conditions. Mars's fate came from the interaction of its size, gravity, solar exposure, internal evolution, chemistry, and distance from the Sun. The magnetic field mattered, but it was part of a larger vulnerability built into the planet from its formation. Nor did the atmosphere escape only through one process. Solar wind stripping, ultraviolet-driven escape, charged particle loss, and impact erosion all likely contributed. Some carbon dioxide may also have been absorbed into rocks or frozen in buried deposits rather than lost to space. Scientists continue to debate how much ancient carbon remains hidden in the crust and how dense the early atmosphere truly was. There may never have been one enormous atmosphere resembling Earth's. Mars could instead have moved through a series of moderately thick atmospheres, repeatedly reduced and partly restored by volcanism. The surviving evidence supports major loss, but the details of the starting point remain uncertain. For any life that might have existed, the decline of the surface would have been a test of adaptation. Microorganisms in shallow water would face freezing, salt buildup, ultraviolet damage, and increasingly long dry intervals. Some could be buried by sediment and preserved as chemical traces. Others, if capable of moving or spreading through groundwater, might follow liquid water into deeper fractures. On Earth, microbes survive inside rock far below the reach of sunlight, supported by chemical reactions involving hydrogen, sulfur, iron, and water. A Martian biosphere, if one ever developed, may have retreated in the same direction. The surface could become sterile, while life endured in isolated pockets below, separated by miles of frozen ground and stone. But survival would grow harder as underground reservoirs became colder, more saline, and less connected. Habitats that once exchanged material through rivers could shrink into sealed chambers, each one a small world with limited energy. Extinction might happen region by region rather than everywhere at once. Some environments could persist for millions of years after the last open lake disappeared. Others might remain potentially habitable even today. Yet that possibility creates a difficult problem for exploration. The deeper and safer the habitat, the harder it is for a rover on the surface to reach. By the time the Great Wet Age had ended, Mars had not lost every trace of water. It had hidden it. Ice remained beneath the soil, inside glaciers covered by dust and rock, and within the polar caps. Water became chemically bound in minerals. Perhaps liquid reservoirs survived at depth, where pressure and geothermal heat were sufficient. From orbit, the planet would still appear dynamic, with dust moving across plains and frost advancing with the seasons. But the open waterways were largely gone. River deltas hardened into stone. Lake beds became exposed to radiation. Organic molecules near the surface began breaking apart under cosmic rays and ultraviolet light. The records most likely to survive were buried records, sealed beneath sediment before the atmosphere became too thin to protect them. This is why the death of Mars did not erase its earlier promise completely. The same sediments that marked the retreat of water may have entombed whatever chemistry existed before it. Each drying lake became both a grave and an archive. Each abandoned delta held material carried from distant terrain and covered it layer by layer. If microbes had lived in those waters, their most durable traces might remain not where the planet stayed active, but where activity ended gently enough for mud to settle over them. Mars had crossed from a world shaped by flowing water to one shaped mainly by wind, ice, radiation, and time. Yet beneath the desert, the old planet had not vanished. Its water was still there in altered forms, its ancient atmosphere recorded in minerals and isotopes, its lost magnetic field frozen into fragments of crust. Even its possible life, if it had ever existed, might not have disappeared entirely. As the surface became colder and more exposed, the final refuges would have moved downward into a hidden Mars untouched by daylight, a world beneath the world, where the last habitable spaces may have survived long after the rivers above had turned to dust. If anything survived the collapse of the Martian surface, it would not have survived in the open. The last reliable refuges would have been below, beyond the reach of ultraviolet light, shielded from cosmic radiation, insulated from violent temperature swings, and close to the one resource that Mars never completely lost: water, hidden inside the planet itself. From above, modern Mars appears almost perfectly dry, a world of dust, fractured stone, and frost that vanishes with the seasons. But the surface tells only the shallowest part of the story. Radar instruments, neutron detectors, orbital cameras, and exposed cliffs have revealed that enormous amounts of water ice remain locked beneath the ground. Some deposits lie only a few feet below the surface. Others form buried glaciers hundreds of feet thick, concealed beneath protective blankets of rock and dust. In the polar regions, layer after layer of ice preserves a climate record stretching back millions of years. Farther toward the equator, strange flowing shapes and debris-covered ridges resemble glaciers frozen in place, suggesting that Mars once moved ice across its landscape far beyond the modern polar caps. These are not small leftovers. In some regions, the volume of buried ice may be comparable to large terrestrial ice sheets. The ancient water did not simply disappear into space. Much of it retreated into cold storage. For a hypothetical Martian organism, however, ice alone would not be enough. Life requires more than the presence of water molecules. It needs access to liquid, energy, nutrients, and enough stability to maintain metabolism. The surface rarely provides that combination today. Atmospheric pressure is so low that exposed liquid water is unstable, while temperatures are usually far below freezing. Salts can lower the freezing point, and thin films of briny water may occasionally form under special conditions, but the evidence for persistent surface brines remains uncertain. Features once interpreted as seasonal streams, including dark streaks descending warm slopes, are now often explained by dry flows of sand and dust rather than running water. Mars repeatedly tempts observers with shapes that resemble activity, only to reveal that geology can imitate life and water with remarkable precision. Deeper underground, the rules change. Pressure rises with depth, temperature becomes more stable. Radiation weakens rapidly as rock absorbs it. A few feet of soil can provide significant protection, while several yards of stone would block much of the destructive radiation that reaches the surface. Go deep enough, and geothermal warmth from the planet's interior may raise the temperature toward conditions where salty water can remain liquid. Mars has cooled greatly, but it is not entirely geologically dead. Volcanic regions such as Elysium Planitia show evidence of activity that may be surprisingly recent in geological terms, and the detection of Marsquakes demonstrates that the interior still shifts and releases energy. Heat escaping from below is weak compared with early Mars. Yet even a weak heat flow can matter when trapped beneath thick layers of insulating rock and ice. A fracture containing brine does not need to resemble an underground lake. It may be no more than a thin, wet boundary between mineral grains, a pocket inside porous stone, or a slow seep moving through a fault. On Earth, microbes inhabit exactly such environments. They live miles below the surface in darkness, isolated from sunlight, and sometimes cut off from the atmosphere for immense spans of time. Their energy comes from chemistry. Hydrogen produced when water reacts with rock, sulfur compounds, iron, methane, and natural radiation breaking water molecules apart. These organisms grow slowly, sometimes dividing only after years or decades. Yet they prove that a biosphere does not need forests, oceans, or even direct contact with the surface. It needs a chemical imbalance that can be exploited. Ancient Martian crust may have provided many of them. Water, moving through iron-bearing minerals, could produce hydrogen. Volcanic gases could supply carbon compounds and sulfur. Radioactive elements inside rock could split water and create usable energy. The boundary where two types of groundwater met might sustain reactions for long periods, even after the atmosphere above had become almost irrelevant. If Martian life began in lakes or hydrothermal systems, the underground would have been the obvious direction of retreat. As surface water froze, organisms capable of surviving in sediment pores might follow moisture downward. Some could remain dormant during cold intervals and reactivate when heat or groundwater returned. Others might adapt to increasing salt concentrations as liquid reservoirs shrank. But this retreat would not have been simple or guaranteed. Salt preserves liquid at lower temperatures. Yet, extremely salty water can also pull moisture out of cells and disrupt their chemistry. Deep habitats offer protection, but they may lack fresh nutrients. Isolation reduces the danger of environmental change while also cutting organisms off from new energy sources. A refuge can become a prison. Over millions of years, separate pockets of life could be divided by frozen ground, each population slowly exhausting the chemistry around it. One underground chamber might survive, while another, only a few miles away, went sterile. If life remained, Mars would not possess one continuous biosphere. It would contain islands of habitability buried in darkness, separated by distances too great for organisms to cross. Lava tubes may have offered another kind of shelter. Mars contains vast volcanic plains where ancient lava flows hardened on the outside while molten rock continued moving within. When the lava drained away, it left behind tunnels, some potentially much larger than similar structures on Earth, because the planet's lower gravity allowed wider roofs to remain standing. Orbital images show lines of collapsed pits and skylight-like openings that may lead into these hidden spaces. Inside, temperatures would fluctuate less than at the surface, radiation levels would be lower, and ice might persist in permanently shadowed chambers. Yet, a cave is not automatically habitable. It would still need water and a usable energy source. Some lava tubes may be dry and chemically inactive. Others could intersect fractures carrying vapor, frost, or ancient groundwater. If life ever occupied them, traces might remain protected on cave walls or sealed beneath mineral deposits beyond the reach of surface weathering. These places are among the most promising targets for future exploration precisely because they preserve what the exposed landscape destroys. Mars's crust may also contain water in forms that are easy to overlook. Certain minerals hold water within their crystal structures, storing it chemically rather than as visible ice. When rocks are heated or altered, some of that water can be released. This means a dry-looking layer may contain a hidden reservoir unavailable to the eye. Impacts, volcanic intrusions, or slow geothermal heating could occasionally unlock it, creating temporary wet zones below ground. Such events might awaken dormant microbes, if dormancy over those timescales is possible, or simply restart non-living chemistry. The planet's underground history may therefore be episodic, with long frozen intervals interrupted by brief pulses of warmth. These pulses would leave little evidence at the surface, especially after millions of years of erosion and dust deposition. Yet, underground, mineral veins and altered rock could preserve the paths where hot water once moved. The possibility of present-day liquid water became especially controversial after radar observations near the South Pole were interpreted as reflections from subsurface lakes beneath thick ice. The initial reports raised the dramatic possibility that large bodies of salty liquid might exist today. Later studies offered alternative explanations, including clays, saline ice, or unusual mineral layers capable of producing similar radar signals. The debate remains unresolved, and it illustrates the difficulty of studying a hidden planet from orbit. A bright radar reflection is not a photograph of a lake. It is a signal that must be interpreted through assumptions about temperature, composition, and the behavior of buried materials. Even if liquid water exists beneath the pole, its salt concentration and temperature may make it far more hostile than the word lake suggests. Still, the controversy matters because it demonstrates that Mars may contain environments we cannot yet classify from above. Every instrument sees only part of the truth. Methane has added another layer of uncertainty. Small amounts have sometimes been detected in the Martian atmosphere, including local variations measured near the surface, while other instruments have failed to find it at expected levels. On Earth, much methane is biological, but it can also be produced by geological reactions between water and rock. If methane is truly being released on Mars, it could indicate active underground chemistry. It would not prove life, and the conflicting measurements remain difficult to reconcile. but it suggests that the subsurface may not be completely inert. Gas could accumulate in buried fractures and escape only when pressure changes or cracks open. A rover might pass near a release and detect it, while an orbiter averaging over a vast region could miss it. Or the methane may be created, destroyed, or trapped through processes not yet understood. Mars continues to offer signals that hover between the ordinary and the extraordinary, never quite allowing the more exciting interpretation to stand alone. Searching for life in these hidden environments creates a serious problem. The safest places for possible organisms are the hardest places to reach. Current rovers can drill only inches into rock, far above the depths where stable liquid water might exist. A mission capable of drilling hundreds of feet or exploring a deep cave would require extraordinary power, precision, and protection from contamination. Any spacecraft sent into a potentially habitable zone would also carry microbes from Earth, unless sterilized to extreme standards. Finding terrestrial contamination in a Martian sample could create the illusion of discovery, while introducing Earth life into a protected environment could damage the very evidence scientists hope to study. The search is therefore not simply a matter of digging deeper. It is a question of how to enter another planet's most sensitive places without rewriting their history. For now, the underground Mars remains largely imagined through indirect evidence. Buried ice mapped from orbit, quakes traveling through the interior, minerals formed by ancient groundwater, volcanic structures disappearing into darkness, and chemical signals that may rise from unseen depths. No living organism has been found. No underground reservoir has been confirmed as a habitat. Yet, the possibility cannot be dismissed. Because the same planet that became lethal at the surface may have preserved habitable conditions below for far longer. If life once existed, it may have endured there after the final lakes froze, surviving not as a thriving world, but as a scattered persistence, slow and almost motionless, hidden beneath miles of silence. And while those possible refuges remained sealed away, another species on a distant blue planet was beginning to look upward, turning the red light in its night sky into gods, stories, maps, imagined canals, and eventually a question powerful enough to send machines across space. For most of human history, Mars was not a world, but a warning in the sky. A restless red point wandering against the fixed stars, bright enough to attract attention and strange enough to invite meaning. Ancient cultures associated its color with blood, fire, conflict, and divine power. But none of them could know that the redness came largely from iron minerals oxidized across its surface. To the unaided eye, Mars revealed nothing of valleys, volcanoes, ice, or buried water. It offered only motion and color, two simple facts that the human imagination quickly turned into personality. The planet became Ares to the Greeks, Mars to the Romans, and a symbol of war long before anyone understood it as a physical place. That began to change after the invention of the telescope, when observers could finally see that the red light had a disk, phases, pale polar caps, and markings that appeared to shift with the seasons. Each improvement in optics seemed to bring Mars closer, yet often made the truth more difficult to separate from expectation. 17th century astronomers mapped dark regions and measured its rotation, discovering that a Martian day is only slightly longer than a day on Earth. Later observers watched the polar caps grow and shrink, a rhythm that made Mars feel almost familiar. If it had seasons, perhaps it had weather. If the dark markings changed, perhaps vegetation was spreading and retreating. A planet that resembled Earth in even a few ways became easy to complete in the mind. The most consequential illusion emerged in 1877, during a favorable opposition when Mars and Earth passed relatively close. Italian astronomer Giovanni Schiaparelli observed a network of narrow-looking lines and called them canali, an Italian word meaning channels or grooves. In English, the term was widely translated as canals, changing a cautious description into something that implied construction. A channel might be natural. A canal required builders. The mistranslation did not create the entire idea of Martian civilization by itself, but it gave that idea a shape people could draw. Soon, maps displayed straight lines crossing continents and linking dark regions, as if an intelligence had organized the planet. Some observers reported seeing the lines split into parallel pairs. Others found new intersections and seasonal changes. Yet many capable astronomers could not see them at all. The disagreement should have weakened the theory, but uncertainty often feeds imagination more effectively than proof. If the lines appeared only under the best conditions, perhaps they were simply too fine for ordinary telescopes. If different observers drew different networks, perhaps Mars was changing. The lack of clarity became evidence of complexity rather than a reason for caution. No one embraced the canal vision more completely than Percival Lowell, a wealthy American who built an observatory in Arizona, partly to study Mars. Through the late 19th and early 20th centuries, Lowell described a drying planet whose intelligent inhabitants had constructed a vast engineering system to carry water from the polar caps toward warmer regions. In his interpretation, the lines were not merely signs of life, but signs of a civilization fighting extinction. Mars became an old world, farther along the path that Earth might one day follow, where survival had forced an entire species to cooperate on a planetary scale. The idea was scientifically weak, but emotionally powerful. It transformed blurry telescope markings into a tragedy unfolding millions of miles away. Lowell's books reached far beyond astronomy, and the Martians of fiction inherited his dying planet even when writers imagined them as enemies rather than desperate engineers. H.G. Wells turned Mars into the source of an invasion in the War of the Worlds, while later stories filled it with ancient cities, deserts, monsters, and ruins. By the middle of the 20th century, Mars already existed twice. Once as a real planet, barely understood through telescopes, and once as a cultural world built from fear, hope, and projection. The first spacecraft forced those two versions to collide. On July 14, 1965, NASA's Mariner 4 flew past Mars and returned the first close photographs of another planet. The images arrived line by line, revealing cratered terrain that looked more like the Moon than the Earth-like world many had expected. There were no visible canals, forests, cities, or open seas. The atmosphere was extremely thin, dominated by carbon dioxide, and the measured surface pressure appeared far too low for stable liquid water in the open. For the public, the result felt like a door closing. Mars was not a neighboring Earth waiting to be recognized. It was cold, dry, and apparently hostile. Yet Mariner 4 had photographed only a small fraction of the surface, and the conclusion that Mars was geologically dead soon proved premature. Later flybys expanded the view, but the greater revelation came in 1971, when Mariner 9 became the first spacecraft to orbit another planet. It arrived during a global dust storm so intense that almost the entire surface vanished beneath a reddish haze. For weeks, only the summits of enormous volcanoes stood above the dust, like islands in an atmosphere-wide sea. When the storm cleared, Mars revealed landscapes far more dramatic than the cratered photographs had suggested. Olympus Mons towering higher than any mountain on Earth, the immense canyon system of Valles Marineris cutting across thousands of miles, layered polar deposits, and channels that looked as though they had been carved by catastrophic floods. The canals were imaginary, but real channels existed, irregular, eroded, and geological rather than engineered. Mars had not been a static desert forever. Water had moved there, perhaps in quantities large enough to reshape entire regions. The question of life returned, but in a different form. Scientists no longer expected cities or vegetation visible from Earth. They began asking whether microbes could survive in the soil, whether chemical activity might reveal metabolism, and whether a world that once possessed water could still contain hidden biology. The Viking missions were designed to confront that question directly. In 1976, 2 orbiters reached Mars, mapping the planet and searching for landing sites, while Viking 1 descended to Chryse Planitia, and Viking 2 followed into Utopia Planitia. Their landers carried cameras, weather instruments, chemical equipment, and 3 biological experiments intended to detect possible activity in the soil. The landscapes they photographed were barren, but not featureless. Rocks lay scattered beneath a salmon-colored sky. Frost appeared at the Viking 2 site. Winds shifted dust around the stationary machines. Nothing moved that resembled an organism. But the search had never depended on seeing one. The most famous experiment, known as labeled release, placed a small Martian soil sample inside a chamber and added liquid nutrients containing radioactive carbon. If microorganisms consumed the nutrients and released gas, the instrument could detect the radioactive products. Soon after the nutrient was added, the experiment registered a rapid release of gas. When a control sample was heated strongly before receiving the nutrients, the response disappeared, a result that at first seemed consistent with biological activity destroyed by sterilization. For a brief moment, a machine on Mars appeared to have detected something alive. But the other experiments complicated the picture. The gas exchange experiment exposed soil to water and nutrients, looking for gases associated with metabolism, while the pyrolytic release experiment tested whether organisms might use light and atmospheric carbon to create organic matter. Their results were suggestive in some respects, but inconsistent and difficult to interpret. Most damaging was the gas chromatograph mass spectrometer, which heated soil in an attempt to identify organic compounds. It found no clear indigenous organic material at the levels expected near the surface. If microbes were producing the labeled release signal, why did the soil appear almost empty of organics? Scientists increasingly favored a non-biological explanation. The Martian soil contained highly reactive chemicals capable of breaking down the added nutrients and releasing gas without life. The surface, exposed for ages to ultraviolet radiation, could manufacture powerful oxidants. Decades later, the Phoenix lander detected perchlorate salts in Martian soil, and researchers realized that heating perchlorate-bearing samples could destroy organic compounds or transform them into products that Viking might not have recognized correctly. This discovery complicated the old interpretation of the mass spectrometer, but it did not turn the Viking results into proof of life. Perchlorates can help explain both why organics were hard to detect and why the soil behaved so reactively. Gilbert Levin, the principal investigator of the labeled release experiment, continued to argue that the biological interpretation had been rejected too quickly. Most researchers remained unconvinced because extraordinary evidence must survive competing chemical explanations, and Viking had produced no independent confirmation that cells, biological structures, or unmistakably biological molecules were present. The mission had reached the surface with instruments designed before scientists understood how chemically unusual Martian soil might be. It asked a direct question: is there life here? But nature answered in a language the instruments could not fully translate. Viking therefore became neither a confirmed discovery nor a simple failure. It exposed the danger of searching for biology before understanding the environment that might imitate it. A reactive mineral can release gas. Heat can erase the very organic matter an instrument is trying to detect. A chemical response that looks like metabolism may have nothing to do with a cell. At the same time, the absence of a clear result at 2 landing sites could not prove that the entire planet was sterile, especially if life had retreated beneath the radiation-damaged surface or disappeared billions of years earlier. The experiment changed the strategy of Mars exploration. Rather than landing again with the same question, scientists stepped backward to build a more reliable path. First, follow the water. Then, determine whether ancient environments were habitable. Next, search for organic chemistry and rocks capable of preserving biological traces. Only after geology, climate, and chemistry were understood together could a possible biosignature be judged without repeating Viking's ambiguity. The imagined canals had taught humanity how easily the mind could create evidence from uncertain images. Viking taught a subtler lesson. Even real data can mislead when the planet's chemistry is unfamiliar. Mars had moved from mythology to observation, from observation to illusion, and from illusion to direct experiment. Yet the central mystery remained intact. The civilization was gone because it had never been there, but the possibility of simpler life had become harder to dismiss. Beneath the rocks photographed by Viking lay a history of rivers, lakes, and buried environments the landers had not been equipped to read. To search that deeper history, the next generation of machines would stop asking the soil for an immediate yes or no. They would learn to read Mars layer by layer, following the evidence of water toward the ancient places where a living world, if it ever existed, might have left something behind. After Viking, the search for life on Mars did not end. it became more patient. Scientists had learned that a single chemical reaction in unfamiliar soil could raise more questions than it answered. So the next generation of missions would not begin by asking whether anything was alive. They would first reconstruct the planet that had existed before the desert, follow the minerals formed by water, map the buried ice, examine ancient sediments, and search for places where evidence might have survived. The strategy sounded less dramatic, but it changed Mars more completely than any imagined canal ever had. In 1997, Mars Pathfinder descended beneath a parachute and airbags into Ares Vallis, a broad plain shaped by ancient flooding, carrying a small rover named Sojourner. Barely larger than a microwave oven, it could not travel far or drill deeply, yet its movement across another planet marked the beginning of a new kind of exploration. Instead of studying one patch of soil beneath a stationary lander, a robot could approach different rocks, compare their chemistry, and make decisions based on what it encountered. Pathfinder found rounded stones and mixed deposits consistent with powerful floods that had swept material from distant regions. The evidence did not prove that the landing site had once been a peaceful river valley. The water may have arrived catastrophically, rushing through the landscape before vanishing. But the plain was clearly not shaped by wind alone. Mars had moved water with enough force to transport boulders and reorganize the ground beneath Sojourner's wheels. While the little rover explored below, Mars Global Surveyor began transforming the view from orbit. Its laser altimeter measured the height of nearly the entire planet, revealing the enormous contrast between the cratered southern highlands and the lower northern plains with unprecedented precision. Its camera photographed gullies, layered deposits, channels, and sedimentary structures in enough detail to guide future landing sites. Even more surprising was its discovery of magnetic stripes locked inside ancient crust. These bands suggested that early Mars once possessed a global magnetic field, and that parts of its crust had formed while that field was still active. Some researchers considered whether the pattern might even hint at movement within the ancient crust, though clear evidence for Earth-like plate tectonics remains lacking. What mattered was that Mars had once been internally more dynamic, protected by a magnetic shield that later disappeared. The planet's surface history was beginning to connect with its interior decline. Then Mars Odyssey arrived in 2001, carrying an instrument capable of detecting hydrogen near the surface. Across broad regions, especially at high latitudes, it found far more hydrogen than dry rock alone could explain. The most convincing interpretation was water ice buried beneath a thin layer of soil. Mars was not simply a world that had lost all its water to space. Vast quantities remained hidden underground, frozen beyond direct view. The discovery changed where scientists imagined the missing water had gone, and prepared the way for a lander designed to touch it. Meanwhile, Europe's Mars Express entered orbit in 2003 and began identifying minerals across the planet. Clay-bearing rocks appeared mainly in very ancient terrain, recording an early period when water interacted with the crust under relatively moderate conditions. Sulfate minerals became more common in younger deposits, often associated with acidic, evaporating water. Still later surfaces were dominated by iron oxides formed under dry conditions. The pattern was not a perfect universal sequence, but it revealed a broad transformation. Ancient Mars passed from water-rich alteration toward increasingly acidic and arid environments. Geological eras that once existed only as crater counts were becoming chemical chapters. The same year Mars Express arrived, NASA sent 2 rovers to opposite sides of the planet. Spirit landed in Jezero Crater, a basin connected to what appeared from orbit to be an ancient river channel. Scientists hoped to find lake sediments immediately, but the plains around the landing site were covered mainly by volcanic rock. Mars had hidden the expected history beneath later lava. Spirit had to climb into the Columbia Hills before encountering stronger evidence of water. There, it found altered rocks, sulfate-rich soils, and deposits of nearly pure silica. On Earth, concentrated silica can form through interaction with hot water or acidic steam near volcanic systems. Spirit could not determine a unique origin, but the discovery suggested that Gusev once contained hydrothermal environments where heat from below met water in the crust. Such locations are valuable because they provide chemical energy and can preserve traces of microbial ecosystems. Spirit's greatest lesson came from what it found only after the obvious interpretation of the landing site failed. Water on Mars had not created one uniform world. It appeared in rivers, lakes, hot springs, groundwater systems, and volcanic settings, sometimes buried beneath landscapes that looked completely unrelated from above. Opportunity landed in Meridiani Planum and almost immediately entered a different chapter of Martian history. The rover rolled into a small crater whose exposed bedrock contained tiny spherical objects nicknamed blueberries. These spheres were rich in hematite and had likely formed when mineral-bearing groundwater moved through porous rock and deposited material around small centers. The surrounding layers also contained sulfate salts and textures indicating that liquid water had repeatedly entered the ground and sometimes reached the surface. Ripple-like patterns in the rock suggested shallow, flowing water, though the environment was probably salty and acidic rather than a gentle freshwater lake. Opportunity had found a place where water was undeniable, but not necessarily friendly to life. This distinction became essential. A wet environment is not automatically habitable, just as a dry one is not automatically sterile. Chemistry determines whether water supports complex molecules or destroys them. Meridiani may have challenged organisms with acidity, salt, and oxidation. Yet microbes on Earth survive comparable extremes. Opportunity continued moving for nearly 15 years, crossing plains, descending into craters, and studying layers that represented changing conditions over immense spans of time. Its endurance turned a landing site into a regional geological survey. In 2008, the Phoenix lander touched down near the northern polar region and scraped through the soil with a robotic arm. Bright material exposed in a trench disappeared over several days, behavior consistent with water ice sublimating directly into vapor. Phoenix had reached the reservoir Odyssey had detected from orbit. The lander also identified perchlorate, a reactive salt that would later reshape interpretations of earlier missions. Perchlorate can lower the freezing point of water, allowing extremely salty liquid to exist under colder conditions. But it can also destroy organic molecules when heated during laboratory analysis. This raised the possibility that Viking's search for organics had been complicated by the chemistry of the soil itself. The planet had not merely concealed evidence, it may have altered it during the act of measurement. As these landers worked, the Mars Reconnaissance Orbiter began photographing the surface at extraordinary resolution. Its instruments mapped clays, carbonates, sulfates, hydrated silica, and other minerals formed or changed by water. Ancient deltas emerged in crisp detail. Sedimentary layers appeared inside craters and canyons. Some regions revealed rocks so old that they may record conditions from the first several 100 million years of Martian history. The orbiter did more than find water-shaped landscapes. It allowed scientists to select sites where different pieces of the habitability puzzle overlapped: persistent water, protective minerals, fine sediment, and geological access for a rover. That search led to Gale Crater and the arrival of Curiosity in 2012. Curiosity was not designed to detect living organisms directly. Its central task was to determine whether ancient Mars had ever offered an environment capable of supporting them. Soon after landing, it found a streambed containing rounded pebbles cemented into rock. It then drove toward Yellowknife Bay, where it drilled into mudstone formed from fine sediment deposited in an ancient lake. The sample contained clay minerals and essential elements including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The chemistry suggested water that was not extremely acidic or overwhelmingly salty. It also contained minerals in different oxidation states, creating the kind of chemical energy gradient that microorganisms can exploit. For the first time, a rover had identified an ancient Martian environment that was not merely wet, but broadly habitable by the standards of simple Earth microbes. Nothing in the sample proved that life had occupied the lake, but the old question had changed. Scientists no longer had to ask whether Mars ever possessed the necessary conditions. At Gale, at least, many of them had existed together. Curiosity then began climbing Mount Sharp, the layered mountain rising from the crater's center. Each layer represented a different interval of environmental change. Clay-rich rocks recorded sustained interaction with water. Higher sulfate-bearing layers suggested evaporation and increasing dryness, though evidence of later groundwater showed that water did not vanish in one clean retreat. The rover found organic molecules preserved in ancient mudstone, including carbon compounds that had survived billions of years inside the rock. These molecules could have formed through geological reactions, arrived in meteorites, or been connected to biological processes. The rover could not determine which. Curiosity also measured changing amounts of methane near the surface, including occasional spikes that remained difficult to explain. On Earth, methane often comes from life, but it can also form when water reacts with certain rocks. Orbital instruments have not consistently detected the same gas, leaving open questions about whether Martian methane is produced locally, destroyed rapidly, released seasonally, or affected by an unknown process. The result is intriguing precisely because it refuses to become evidence by itself. After decades of exploration, the robots had assembled a lost world from fragments. Water had flowed through open channels, flooded plains, filled lakes, altered volcanic rocks, circulated underground, frozen beneath the soil, and left behind minerals that recorded changing climate. Mars had possessed multiple habitable environments rather than one brief, wet episode. Yet every discovery sharpened the absence at the center of the story. The rovers found the house furnished, the water supplied, the chemistry active, but no unquestionable sign that anyone had ever lived there. Perhaps radiation erased the traces near the surface. Perhaps the best evidence remained sealed inside rocks too complex for a rover to analyze fully. Perhaps Mars had approached life without crossing the threshold. To go further, scientists needed more than another photograph or chemical hint. They needed carefully selected pieces of the ancient planet, collected from a place where a river had delivered material into a lake and buried it within a delta. The next robot would enter that archive not only to study the rocks, but to drill them, seal them, and preserve them for a future investigation capable of deciding whether Mars had left behind the closest thing yet to a biological fingerprint. By the time Perseverance reached the ancient river deposits of Jezero Crater, the search for life on Mars had entered its most dangerous stage. Not dangerous for the rover, but dangerous for human certainty. For decades, every promising clue had carried two possible stories. Water could carve a valley, but water alone was not life. Organic molecules could survive in rock, but they could also form without biology. Methane could rise from microbes or from reactions deep underground. Mars had become a planet where the evidence repeatedly approached the extraordinary, then stopped just short of it. Perseverance was sent to narrow that distance. Jezero had once held a lake, and the river that entered it built a delta from sediment carried across the surrounding landscape. On Earth, deltas are among the best places to preserve traces of ancient organisms because mud can bury organic material quickly and protect it from destruction. The rover therefore moved through an archive shaped by water, examining rocks whose grains may have settled when Mars still possessed environments capable of supporting microscopic life. Its instruments could photograph textures smaller than a grain of salt, identify minerals, search for carbon-bearing compounds, and select cores for storage inside sealed titanium tubes. Yet even this laboratory remained limited by what could fit on a machine operating millions of miles from Earth. The discovery that brought the question closest to the surface appeared in July 2024 along the northern edge of an ancient channel called Nedetva Vallis. There, Perseverance encountered an arrowhead-shaped rock 3 feet long, nicknamed Cheyava Falls. White calcium sulfate veins crossed its reddish surface, evidence that water had once moved through fractures in the stone. Between those veins lay pale marks ringed with dark material, soon described as leopard spots. The rover also detected organic compounds within the rock. None of these features alone was shocking. Veins formed through groundwater. Organic carbon can be delivered by meteorites or generated through non-living reactions. Mineral spots can arise from ordinary chemistry. What made Cheyava Falls different was the way several features appeared together. Detailed measurements linked the spots to iron and sulfur-bearing minerals, including vivianite and greigite, arranged along reaction fronts where the rock had undergone chemical change. On Earth, Comparable mineral associations can form when microorganisms exploit reactions involving iron and sulfur, leaving altered zones in sediment. That resemblance is why researchers described the rock as containing a potential biosignature, a deliberately cautious term for a feature that could have a biological origin, but still demands alternative explanations and stronger evidence. NASA announced the peer-reviewed interpretation in September 2025, while emphasizing that non-biological processes had not been eliminated. The biological possibility is compelling because Cheyava Falls appears to have formed where water passed through fine-grained sediment and drove reactions capable of supplying energy. A microbial community, had one existed, might have used those chemical differences much as certain organisms do in mud on Earth. The spots could then represent tiny zones where life altered the surrounding minerals. But resemblance is not identity. Heat, pressure, and fluid moving through rock can produce complex patterns without a single living cell. The rover cannot fully reconstruct the temperature at which every mineral formed, chemistry of the ancient fluids, or every later event that modified the rock. Cheyava Falls therefore stands in an uncomfortable but valuable position. It is more than a random curiosity, yet less than proof. Its importance comes from how difficult the full pattern is to explain, not from the impossibility of explaining it without life. Perseverance drilled a core from the rock and sealed it inside a tube, naming the sample Sapphire Canyon. That small cylinder of Martian stone may contain the best preserved version of the evidence. Inside laboratories on Earth, scientists could examine its minerals at scales beyond the rover's reach, map carbon isotopes, search for molecular structures, test whether organic matter is concentrated around the spots, and look for microscopic textures formed at the same time as the rock rather than introduced later. The sample is already collected, but it remains on Mars while plans for returning selected tubes continue to be developed. NASA has been evaluating competing mission architectures intended to lower the cost, risk, and complexity of bringing the material home, meaning the most decisive evidence may exist inside a sealed tube that no human laboratory can yet touch. While Perseverance examined Jezero, curiosity continued opening a different window into ancient Mars from inside Gale Crater. In March 2025, researchers announced that the rover had detected decane, undecane, and dodecane in an ancient mudstone sample known as Cumberland. These long-chain hydrocarbons were the largest organic molecules then identified on Mars and may be fragments of fatty acids altered during Curiosity's heating process. Fatty acids are important components of cell membranes on Earth and are produced extensively by living systems, but they can also arise through geological chemistry. Their discovery did not demonstrate ancient organisms. It showed that unexpectedly large carbon structures could survive for billions of years inside Martian rock. It also suggested that the original molecules may have been larger before radiation, oxidation, and the rover's analysis broke them apart. The picture became richer in April 2026 when NASA reported that further analysis of a rock drilled by Curiosity in 2020 had revealed 21 carbon-containing molecules, 7 never previously detected on Mars. It was the most diverse collection of organic molecules identified on the planet at the time. These compounds expanded the known range of Martian carbon chemistry, yet they again stopped at the same boundary. Scientists could not determine whether their ultimate source was biological, geological, delivered from space, or some mixture of all three. Another NASA-supported analysis, published in early 2026, argued that the amounts and patterns of certain organics were not fully explained by the non-biological degradation scenarios tested, but that conclusion did not convert them into evidence of life. It revealed gaps in the chemical models. This is where the search becomes more difficult than simply finding carbon. Life does not own organic chemistry. Interstellar clouds, meteorites, volcanic systems, and reactions between water and rock can all produce carbon-bearing molecules. Even structures associated strongly with biology on Earth may have non-living routes under conditions unlike those on our planet today. A convincing Martian biosignature would therefore need several independent clues preserved together: organic compounds with meaningful patterns, minerals formed under suitable conditions, isotopic ratios difficult to generate abiotically, microscopic textures consistent with growth or metabolism, and a geological context proving that all of them formed at the same ancient moment. The evidence would also need to survive contamination checks and repeated analysis by independent laboratories. One exciting feature would never be enough. Mars has spent decades demonstrating why. Each clue is real, but the interpretation remains vulnerable until every ordinary pathway has been tested. Three broad possibilities now remain open. The first is that life emerged during Mars's wet era and left traces that still survive in rare protected rocks, such as Cheyava Falls or the mudstones of Gale. In that case, the planet may have hosted a microbial biosphere that vanished as surface conditions deteriorated, or retreated underground, where isolated habitats could conceivably persist. The second is that Mars developed rich prebiotic chemistry, but never crossed the threshold into self-replicating evolution. Its lakes may have contained complex molecules, mineral catalysts, and chemical energy while remaining entirely lifeless. That outcome would be almost as important as discovering biology, because it would show that habitability and life can remain separated, even on a planet with water and time. The third possibility is that evidence once existed but has been damaged beyond recognition. Radiation has struck exposed rock for billions of years. Oxidants have attacked organic matter. Groundwater has altered minerals. Impacts have heated, fractured, and buried the crust. A living Mars might have left a record so faint that modern instruments can detect only ambiguous remnants. The final answer may therefore depend as much on preservation as on biology. If future laboratories find a convincing biosignature in Sapphire Canyon or another returned sample, the consequences would reach far beyond Mars. It would suggest that life arose at least twice within one solar system, unless Martian and terrestrial organisms shared an origin through rocks exchanged between the planets. Independent life would imply that biology may begin readily when conditions permit. A shared ancestry would reveal that planets can exchange more than stone, turning neighboring worlds into connected chapters of one biological history. But a careful search that finds no life would not prove the universe empty. It might instead show how rare the transition from chemistry to biology truly is, or how easily time erases the evidence. Mars has already answered the question of whether it once possessed rivers, lakes, deltas, organic carbon, and environments that microbes could have inhabited. It has not answered whether anything used those opportunities. The strongest evidence now rests in patterns of minerals, ancient organic molecules, and sealed pieces of rock waiting under a cold sky. They do not allow us to say that Mars held life 3.5 billion years ago. They allow us to say something more precise and perhaps more haunting. Mars reached conditions close enough to life that the difference between a living world and an empty one may now be hidden inside structures smaller than dust. Somewhere within those samples lies either the first evidence that life began beyond Earth, or the record of a planet that possessed nearly everything and still remained silent. Until the stone itself can be studied in full, Mars keeps both histories alive. Mars may still be hiding the answer to one of humanity's greatest questions. Did life ever begin beyond Earth? Until those ancient rocks reveal their secrets, the mystery remains. If you enjoyed this journey, please like the video and subscribe to Sleepy Cosmic Lore. Your support truly helps the channel grow. Thank you for watching, and good night.